Okay, welcome back. There's a couple of different modeling notations for entity relationship. One is the Chen notation. That's the one I most commonly use myself. Chen was a gentleman who developed the entity relationship modeling method. And you can see here that in the Chen notation, entities are represented by rectangles and relationships by diamonds. Then you also have another popular one is crow's foot. The entities are represented by rectangles again, but you have a line with a different end terminal. And you see here a crow's foot on one end meaning many and a single line to the other painter. So one painter does many paintings, but a single painting is only done by one painter. And then the universal modeling language class approach is yet another. They're all, pretty intuitive to see. When you see it, it makes sense what you're looking at. So another class participation question. What is a relationship, and what three types of relationship exist, and give an example of each one? Okay, I think you guys nailed that. Let's just go over it. A relationship is an association between two entities. You can have a one-to-one, and that's where one record in one entity goes to one record only in the other, and vice versa. So we mentioned an academic department is chaired by one professor, and a professor may chair only one academic department. Another type of relationship is a one-to-many. So one department can have many students, but one student will only belong to one department. And then we can have a many-to-many. So one student can take many courses, and one course can have many students. Once the relational model became established and databases began getting a good reputation, a lot of companies tried other approaches rather than the relational model approach. And one of those was the object-oriented data model. And there was a few implementations of that, but it never really became widespread. It didn't make a dent in relational database hegemony for the last 40 years. And I think the reason is because the whole idea of object-oriented systems is to hide the data from the user. So you can't get to the data directly. You have to go through methods in an object. So it's hiding the data, and that seems completely the opposite of what you want to do in a database. In a database, you want to make the data easily accessible by people who have the authorization to do that. But like in all object-oriented systems, you have a class, and the class has methods or routines that let you access the data, update the data, things of that matter. And it has some valuable aspects like inheritance. So again, it didn't really take off. And then one of the things, high system overhead slows transactions. Yeah, because you're not going directly to the data, you're going to an object and then to the data. So it's like twice as long. and UML class diagram, one of the things that did become widespread, obviously object-oriented programming became widespread, but with regard to databases, some of the class diagram notation became integrated in with the entity relationship modeling notation. And then you had object relational and XML. Most databases do implement XML, and now they have kind of switched that into JSON, JavaScript object notation, which is a way of transmitting data. And JSON is like much more efficient than XML. But it's just a way of transmitting the data from one location to another. So let's think about how the entity relationship model helped produce a more structured relational database design environment. I'll take this one. The entity relationship model, or ERM, helps identify the database's main entities and their relationships. Because the ERM components are graphically represented, their role is more easily understood. Using the ER diagram, it's easy to map the ERM to the relational database's tables and attributes. This mapping process uses a series of well-defined steps to generate all the required database structures. Okay. Consider the scenario described by this statement. A customer can make many payments, but each payment is made by only one customer. So, as the basis for an entity relationship diagram representation, use Chen's notation to draw this. So go ahead and take a minute and draw what you think it should. Okay, let's take a look at what it should look like. So we have a customer, and a customer can make many payments. We see the M over here indicating many, but one payment will only be made by one customer. So we see the one over there. And of course, entities are rectangles, relationships are diamonds. So why is an object said to have greater semantic content than an entity? Well, again, I'll take this one. An object has greater semantic content because it embodies both data and methods or procedures. That is, the object contains, in addition to data, also operational procedures that may be performed on the object. So that gives it a little richer semantic depth. Okay, well, relational databases went along fine for 25 years or so. There's really no need to not use relational databases. And then in the early 2000s, e-commerce had become widespread, and the e-commerce sites were dealing with global customer bases and millions of online users at any given time. And so that led to the need for big data. And the characteristics of big data are volume, velocity, and variety. So volume is a lot of data has to be stored. This is expensive, and to do analysis on that, the online analytical processing tools that we had in the past are not able to deal with that kind of volume. So what do the 3 V's refer to? I'll take this one again. The term 3 V's refers to the 3 basic characteristics of big data databases. They are volume, and that refers to the amount of data being stored. With the adoption and growth of the internet and social media, as well as e-commerce, companies have multiplied the ways they can reach out to customers. And over the years, and with the benefit of technological advances, data from millions of e-transactions were being stored daily on company database. Unbelievable what Amazon deals with on a daily basis. Moreover, organizations are using multiple technologies to interact with the end user, and those technologies are generating mountains of data. You might have applications on cell phones. So in addition to taking the customer's order, they find the location they're at. Then there's just other things like that. So there's an ever-growing volume of data that quickly reached petabytes in size, and it's still growing. Velocity is the second V, and it refers to the speed with which the data grows, but also the need to process the data quickly in order to generate information and insight. So with the advent of the internet and social media, business response times have shrunk considerably. Organizations not only need to store large volumes of data quickly, but also need to process such data quickly. So the velocity of data growth is due to the increase in the number of different data streams which are being piped into the organization through the web, e-commerce, Facebook posts, tweets, emails, sensors, GPS, and so on. The third V is variety. Refers to the fact that data being collected comes in multiple different data formats. A great portion of these data comes in formats not suitable to be handled by the traditional operational databases of the relational model. So that led to a couple of new technologies: Hadoop for doing analysis on massive amounts of data. And Hadoop was so slow, it was really batch-oriented only. It's being supplanted by Spark, which is about 100 times faster and can scale to the same levels as Hadoop. And of course, NoSQL that we talked about last week. These are able to scale as well. They're very powerful distributed database systems, and we'll talk about them towards the end of the course. But for now, you need to know that NoSQL databases are, in fact, unlike object-oriented and object-relational and all those things, NoSQL databases actually fulfill a necessary function, and they are growing very rapidly. So let's go ahead, think about the big data phenomenon, and we'll discuss it. Okay, you guys, I think, have a good idea. Many of you actually have used some of this in your work. Big data refers to a movement to find new and better ways to manage large amount of web-generated data and derive business insights from it. At the same time, it's providing high performance and scalability at a reasonable price. So NoSQL databases are not tabular. They use other formats, and they relax some of the key principles of relational databases. One of them is immediate consistency. You have multiple databases that are the same database, but you put them on different servers so that you can scale and handle more traffic. In a SQL database, anytime one of them is updated, they all have to be updated at the same time. This is not the case with NoSQL databases. They have something known as eventual consistency. So you update a record in one of the many copies of the same database on one server, eventually it'll propagate itself to the others. So this isn't going to be, NoSQL is not going to be a database you can use in many use cases, but there are use cases where it's extremely powerful. So the big thing in NoSQL, in terms of data consistency, it provides an eventually consistent model. Okay, so let's define and describe the basic characteristics of a NoSQL database. Well, NoSQL databases are geared towards performance rather than transaction consistency. So it's not based on the tabular relational model and their principle of immediate consistency. NoSQL databases are generally based on a variation of some sort of key value data model. And the key value model is based on a structure where you have two data elements, a key and a value. For every key, there's a corresponding set of values. The key value model is also referred to as the associative data model. And the most popular form of the key value data model is a document model. And so here we see a simple key value model. You have the driver ID, and you have certain certs and their date of birth and their license type, certifications for driving certain types of trucks. So here's the evolution of database models. The models themselves have developed up through entity relationship, and we started looking at semantic models. And now, as of the early 2000s, we're looking at NoSQL models. And some of the terminology comparisons between the different models are here. Like a group of something, let's say in this case, a group of vendors. In file processing, that would be a file. In the hierarchical model, it'd be a segment type. In the network model, it'd be a record type. In relational model, it'd be a table. And in the entity relationship model, an entity set. And in the OO model, a class. So we have various levels of data abstraction. The physical model is extremely concrete. You're choosing a vendor. That vendor has a specific way of storing data on a disk. Then you have the internal model, which is the logical model of the database. It's for us using relational databases. It would be a tabular structure. And then you have the conceptual model where you don't have a lot of the details, like it's an integer or it's a string. You just have, it's the entity of a student, and we collect the attributes of their name, their ID, their total credits, and their department. So the external model is the end user's view of the data. So here's an example of an external model for university. And we take, little subsets of the overall tables and look at them. A conceptual model is a basis for identification and high-level description of the main data objects in your system. A logical design is the task of creating this conceptual data model. So here we're putting in a little bit more detail in our relationships. You can see with the crow's foot, we have one-to-many relationships defined. The internal model is the database as seen by the database management system, and it uses the database constructs supported by the chosen database. So for example, relational databases use table constructs. And so here we take the conceptual model that we can talk to users with fairly easily, and we create our internal model, where we start doing things like defining domains and constraints. Professor's name is a character up to 15 characters long, and so on with the other create table statements. And the physical model operates at the lowest level of abstraction, and it's the way the data is saved onto storage media, which is disks. And we have the degrees of abstraction from low to high, goes physical, internal, conceptual, and external. So let's finish up with a question. What is physical independence? So give it a thought and we'll go over it. Okay, let me summarize it for the folks online. You have physical independence when you can change the physical model without affecting the internal model. So a change in storage devices or methods, or even a change in the operating system, will not affect the internal model. Okay, any questions? All right, see you next week.